Okay, guys, so this video is going to be a little weirder because I'm at home. I don't think it makes sense for me to be in the video presenting it to you. Anyway, I won't be in the video, so I'm sorry, but all you'll get is my disembodied voice. Okay, so we have to talk about the periodic table. We've talked a little about how it's organized by electrons in our last unit. And first, I'd like to show you some different ways the periodic table can be organized. It all started here with Dmitri Mendeleev. Now, he is known as the father of the periodic table, but he wasn't the first person to create a table of the elements. But what made his different from the others is that he was like, guys, what if we don't have all the information? What if in 1872 we don't know all of the elements that exist and there could be more discovered in the future? So what made his different is that he put in blank spots in his periodic table, like right here and right here. And these blank spots basically gave us clues to the elements that we didn't have. Okay, this is what the modern Russian periodic table looks like. It kind of looks a little jumbled to me, but maybe that's because I'm used to viewing ours in the columns that ours is organized in. Like, here are the noble gases: helium, neon, argon, krypton, xenon, but that doesn't include Fe or Ru or Os. But they do still have rows over here along the left. Here's the Chinese periodic table. It looks like ours, but in Chinese, and for some reason it's missing helium. That's weird. Now this one looks real weird, but is actually super useful. The Stowe periodic table organizes it according to those quantum numbers we talked about last unit. So at the top, it has n equals 1, or the first row, which, by the way, rows are also called periods. And down here, you can see that it's the s orbital, because it's that same gray color. Next is n equals 2, or the second row, or period. And here we have that s orbital in the middle with lithium and beryllium, and the p orbital going around it, starting in the bottom left: boron, carbon, nitrogen, oxygen, fluorine, neon. Here is a spiral periodic table that still shows the rows and columns just fine, but in a spiral shape. Same thing here, you can still see the rows and columns, but in the shape of a triangle. That's weird. Mayan periodic table is the worst in my opinion. You can barely gain any information here quickly just by looking at it. And the orbital filling table, many of you have already seen the use of this one. Again, it is organized based on those electrons and how they fill those orbitals from 1s to 7p. Okay, here's where I tell you the group names. I'm sure I've mentioned them here and there, but this is where I show you a labeled table of them. Okay, groups are also called columns. One means all the way to the left. Okay, group 1 is called the alkali metals. Group 2 here is the alkaline earth metals. Now this zone here between columns 3 and 12 is known as the transition metals. There is a small group here along the dark black line. These are the metalloids. These are like halfway between metals and nonmetals. So then past the metalloids are the nonmetals in this area. Just a couple more common group names here. The halogens in group 17, that's fluorine, chlorine, bromine, iodine, astatine. And the noble gases are the last group all the way to the right. That's helium, neon, argon, krypton, xenon. The last two groups are on the bottom. The top row is the lanthanides, and the bottom row is the actinides. Okay, so these group 1 elements are very, very reactive. They really want to get rid of their 1 valence electron. These will react violently with water. Yes, there's a YouTube video we can watch on that. No, I don't have any to show you in person. Here we're going to talk about atomic radius. And since we learned in our last unit that the electrons are kind of wildly moving erratically around the atoms, it can be difficult to determine its radius. So the way we measure atomic radius is to measure the distance of the atom bonded with itself between the two nuclei, and then divided by 2. This is basically an estimation, like we're kind of guessing. when we do that, but it's a pretty close guess. Okay, so there is a trend in the periodic table that has to do with atomic radius, and that is that the atomic radius will decrease across a period, meaning it will decrease from left to right, and it will increase going down a group, which also means that it will increase from top to bottom. The radius increases going down because you're adding more principal quantum levels, or rings, if you remember the Niels Bohr diagrams we did. And it decreases going to the right because the more electrons you have, the more shielded the electrons are from the nucleus. Think of it like this. The nucleus is kind of pulling on these electrons. The nucleus is positive, the electrons are negative, right? So with more electrons, the nucleus is able to pull on these electrons just a little bit more, bringing them just the tiniest bit closer to the nucleus. So this gives a small decrease in the atomic radius from left to right. Okay, here is a table of atomic radii to put some numbers to what we're talking about here. You can clearly see that the atomic radius increases from top to bottom, looking at hydrogen, lithium, sodium, etc. And looking left to right, you can see that it decreases, but not by much. So in this way, you are able to compare where two elements are on the periodic table and determine which one has a higher atomic radius. Our next periodic trend is ionization energy. And to give a quick definition here, basically if we have an atom, we can rip an electron off of it and measure the amount of energy it took to remove. And as you might guess, it takes more energy for each electron you take off an atom. Like if you have a carbon atom and you take an electron off of it, it will take more energy to take the second one off every time. Ionization energy tends to increase across a period, meaning going from left to right, and tends to decrease in a group, meaning going from top to bottom. Now, if you're just looking at the top bit here, we are removing electrons from magnesium. And being in group 2, it has 2 valence electrons. We'll talk about that more in our next unit. But magnesium actually wants to give up these 2 electrons, so it'll do that pretty easily. So this is the energy of pulling off 1 electron from magnesium. The energy it takes is 738 kilojoules. Taking off the second electron from magnesium is slightly harder at 1451 kilojoules. This creates a very stable ion of magnesium. What I'm telling you is it really doesn't want to give up another electron, so it tries to hold on to that electron very much. But if we do continue to rip off its third electron, it actually takes more than 7,000 kilojoules. Okay, this graph down here shows the ionization energy for all 12 electrons in magnesium. Basically what I just talked about, but 9 more times. It increases and increases and increases. And this big jump here is when it only has 2 electrons left. Not that it would be stable as that, but it is a noble gas configuration, and those are always more stable than others. Okay, this graph shows removing 1 electron from all of the first 86 elements. This shows you exactly how easy it is to remove an electron from these group 1 elements, lithium, sodium, potassium, rubidium, cesium, because they actually are more stable with it gone. And on the other side, it shows how very stable the noble gases are because they don't ever want to lose their electron. It takes a lot more energy to rip an electron off of helium, neon, argon, krypton, xenon. This is just another way of showing the exact same thing, but you can clearly see ionization energy increases to the right and up the periodic table. The next periodic trend is basically the exact opposite. However, it follows the same trend. Electron affinity is the energy it takes to add an electron to an atom, but it also increases as you go to the right and up the periodic table. As you can see from this graph, the elements at the top don't really care if they gain an electron. Like, that doesn't help them get any more stable. Whereas the elements at the bottom really want to add an electron. And this is a much larger energy difference. This shows you that halogens, like fluorine and chlorine, are more stable after an electron is added to them. Okay, for ionic radii, meaning after the atom has either gained or lost an electron, cations are positive because they've lost an electron, right? And smaller than neutral atoms, while anions are negative because they gained an electron, and much larger than the neutral atom. And here's a little table to illustrate that for you. You can see it still increases going down the group from lithium to sodium to potassium, but the anions are much larger on the right than the cations are on the left. Here is your next VIP for this unit. It shows a summary of all the periodic trends we discussed today. Atomic radius increases as we go down and increases to the left. Electron affinity and ionization energy both increase to the right and both increase going up. And the amount of metallicness of an element increases kind of diagonally towards the bottom left. There's only one trend not on the VIP, electronegativity, which is the ability of an atom to attract electrons to itself. It's kind of like electron affinity, and it does increase in the same way, to the right and up. One difference between them is that there's a whole table just for these, and this is the way we determine what type of bond different atoms have. This is kind of leading into our next unit, but I want you to have at least seen this before we get there. So that's it. With these notes done, we will have an assignment or two posted to Schoology today. Oh, and we should have a quiz over our last unit as well. I think you can get those done by Friday, December 4th. And of course, if you have any questions or problems, make sure you come to office hours, Tuesday through Friday, 1 to 3. And thanks for watching.